Number 85, antimony pentachloride decomposes according to this equation. And then we have this equation right here, SbCl5 gas, which comes to equilibrium with SbCl3 gas plus Cl2 gas. Then they say, an equilibrium mixture in a 5.00 liter flask at 448 degrees Celsius contains 3.85 grams of SbCl5, 9.14 grams of SbCl3, and 2.84 grams of Cl2. How many grams of each will be found if the mixture is transferred into a 2.00 liter flask at the same temperature? Okay, so a couple of things. Once again, brace yourself, guys, because this one's going to be a wild ride. So let's strap on those seatbelts, okay? And me doing this question while I'm sick is going to show you how much I appreciate teaching you guys. All right, so got to get it done. Let's go. So the first thing is I'm going to just write this out, right? So we have SbCl5 gas comes to equilibrium with SbCl3, and that's a gas, plus Cl2, and that's a gas. Okay, so the first thing is always make sure that this equation is balanced. I'm just searching across this equation, and it is balanced indeed, thank goodness. Now, generally, when we're doing equilibrium, right, usually if they were kind, they would give us a K value, right? But there was no K value here. I don't know what the equilibrium constant is. So the first thing I have to do is I have to find out what that equilibrium value is. Then I could find out what's going on when we change the flask. So the first part is, remember, the Kc expression is this one, right? So maybe I'll just put this down at the bottom just for reference. Remember, Kc is the concentration of the products divided by the concentration of the reactants. Only aqueous and gases are allowed in this formula. But I just see, and they're all gases, so we're going to use each and every single compound here and the molecule Cl2. Now, the reason why I'm doing Kc and not Kp is by what they gave me. They gave me grams and they gave me a liter. Remember, concentration, these brackets, it's the same thing as molarity. And remember your molarity formula, guys. Molarity equals moles divided by liters. So I can find the molarity, I can find the concentration. I wouldn't be using Kp because they didn't give me pressure values here. So the first thing is, they gave me grams of all these. I gotta find the moles, right? Because then I could do mole divided by liter. They told us that initially we were in a 5-liter solution. So this on the bottom for all of them is going to be 5.00 liters. Now we just got to find the moles. Well, how do we go from grams to moles? This is going way back, guys. A lot of refresher here. So let's just take it one by one, find out the moles, get the molarity. Okay, so let's do the 3.85 grams of SbCl5 times by the ratio. Throw the unit that you don't want. We're just converting. So if you don't want grams of SbCl5, that goes on the bottom. Grams of SbCl5 and the moles of SbCl5 go up on the top. This is your periodic table. Gram to mole conversion of the same compound, that's periodic table. 1 mole is whatever the mass is on the periodic table. So calcul's out, periodic table's out. Let's find out what SbCl5 is as I'm losing my voice. But all right, so first off, we got to find out where is Sb. Where's antimony? Here it is. 121.8 plus 5 times 35.45. So 299.05. Cancel out the grams. Let's see what we get for the moles. 3.85 divided by that number. So I get roughly 0.01287 moles. And then we have to find out the molarity. So I'm just going to take the moles divided by the 5 liters, right? and then I would have the molarity for at least SbCl5. So I'm going to divide that by 5. Let's see. What happened here? 0.01287 divided by 5. And I guess we'll do sig figs, okay? So 3 sig figs. So we'll say that this is the same as 2.57 times 10 to the negative 3 molarity. Okay, and that's for this one. So I'm just going to say that this is 2.57 times 10 to the negative 3 molarity. Okie dokie. And I just want to double check on that, because if the math is going wrong in the beginning, the whole thing's going to be a little bit messed up. So, and we are good, 2.57. Okay, perfect. So now I just have to do it for the other 2. So let's go for it. I got 9.14 grams of SbCl3. Got to use that periodic table times by the ratio. Gram of SbCl3 goes on the bottom. Mole of SbCl3 goes up on top. 1 mole is whatever it is on the periodic table. 121.8 plus 3 times 35.45. 228.15. Cancel that out. Let's get that math. Then divide it by 5. 9.14 divided by that answer. I get roughly 0.04006 moles. Turning it into molarity, mole divided by liter, it was 5 liters. So 0.04006 divided by 5. I will put this into scientific notation now with the 3 sig figs. So 8.01 times 10 to the 3. Negative 3, and that's molarity. So now I have this one as well. So 8.01 times 10 to the negative 3 molarity. One more. Let's just move this up a little bit. Okay. So 2.84 grams of Cl2 times it by ratio. Grams of the Cl2 go on the bottom. Mole of Cl2 goes up on top. 1 divided by Cl2 is, where's Cl2? 35.45 times 2. 70.9. Cancel out the grams. We have the moles. 2.84 divided by that answer. 0.0. Oh, basically it's the same thing. Is that a coincidence? I don't know. 0.0056 moles divided by the 5 liters. And let's just see. Even with extending it a little bit further, are we going to get the same answer? Probably. Yep. 8.01 times 10 to the negative 3 molarity. And that's going to be over here. Okay, so pause the video, because I have to erase this, obviously, because now we're going to take these equilibrium values and plug them into my Kc to get a number. So pause it if you need to. I'm going to erase all this. Bye-bye. And now let's use this formula and find out our Kc expression. So Kc equals concentration of... concentration of the products, there are 2 of them. So concentration of SbCl3 times the concentration of Cl2. And they're both raised to the first because there's no values here. And anything raised to the first is itself, so I don't really care. And then divided by SbCl5. Ooh, my voice. Let's keep going. Okay, so I will maybe pull this a little bit over here. We're solving for Kc. We have 8.01 times 10 to the negative third for both of these values. And then this is 2.57 times 10 to the negative 3. So let's get it. Kc equals 8.01 times 10 to the negative 3 times 8.01 times 10 to the negative 3. That's basically the same thing squared, right? And then divide all of this by 2.57 times 10 to the negative 3. And we get a Kc value. Let's see. 8.01 times 10 to the negative 3. I'm going to square that. And then I'm going to divide it by 2.57 times 10 to the negative 3. And I guess we'll do 3 sig figs. So I guess I'll put this in scientific notation. 2.50 times 10 to the negative 2. Remember, there are no units for our Kc expression. Okay, so no units for Kc, no units for Kp. And I'm just going to put that number over here. So we now know that our Kc, our equilibrium value, is 2.50 times 10 to the negative second. Okay, so now the question is, how many grams of each will be found if everything is now transferred into a 2-liter flask? So, what do you think we have to do? Well, we have to basically find the new molarities. We have to do the same thing over again, but now instead of the 5-liter flask, we have to find out what these molarities would be in a 2-liter flask. Actually, we have to find out these amount of grams into a 2-liter. So remember when we did everything and divided it by 5? Now we have to do the same thing and divide it by 2. Now let's see if I could perform some magic here, just to save time, because it's literally the same thing, which I will show you in a little bit. The only thing that we basically need is this number right here, right? So I'm going to try, let's see if I can do this. This is like a little experiment. I'm going to try to, actually, let me write this down. 2.50 times 10 to the negative second, right? I'm going to just copy this value just so that I have it. And I just want to make sure this is the right one. Yep, 2.50 times 10 to the negative second. Perfect. Okay. And now what I'm going to do is I'm going to go back, and you're going to see a lot of erasing, but I'm going to go back and I'm going to try to get those numbers because we don't want to do the same math over and over and over again, right? So bear with me here. Let's see if we could go back and see if we can find out the numbers, and we can just swap them out, right? So here we go. We're going back. I don't want to go back too far. Look at that, guys, right? We're going back in time. Blah, 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 blah. Okay, we're almost there. Okay, we're almost there, guys. Here we go. Here we go. Ready? Oh, yeah. Okay. So we need to find the new molarities. And what I'm going to do is we need that Kc value. So look at that. That was the only thing we needed. Now we need to get the new molarities, right? So remember, it's all the same, but now we just need to change it. We're now in a 2-liter flask, so instead of this 5, they're all going to be 2s. So let's do that. Get rid of all these 5s. Wow, that just saved us a lot of time. I'm so proud of my tech savviness. 2.00. I hope you guys understand the point here, right? We need to find the new molarities because we have a larger, or actually we have a smaller volume. So the molarities are just going to change. Okay, so let's erase these. And now, let's figure it out. So 0.01287 divided by 2. Now you can obviously do this procedure over again on paper if you wanted, because that's technically what you would have to do. But I'm just going to go straight from here because we have the information. So I have And I guess we'll do the 3 sig figs here. So this is 3.44, actually, sorry, 6.44 times 10 to the negative 3 molarity. Maybe I'll make that a 3 a little bit bigger. Oh boy. Okay, there we go. 6.44, I just want to double check. Good. Let's do the next one, 0.04006 divided by 2. I guess we'll do 0.0200 molarity. This one, you could say 2.00 times 10 to the negative second, but it doesn't really matter. And then this one I think would be the same thing. Yep. So we'll say 0.0200. Okay. So now, these are your new molarities. So maybe what I'm going to do is pause the video first if you want to write this down. What I need to get rid of is I just want to get rid of this, because this is now useless. Goodbye. And I want to keep these here. So this was at equilibrium. So this was our values that we found out for Kc. Now I'm going to put the new values underneath it, okay? Just in case. We might need these at some point, but let's see. These are our new values, right? And I did them in order. So this was this SbCl5. So now our new molarity is 6.44 times 10 to the negative 3. And then these two are the same, 0.0200 molarity and then 0.0200 molarity. Now the question is, are we at equilibrium? No, right? Once you change the system, you shock the system, we lowered our volume, we're not going to be at equilibrium anymore. We're going to try to get back to equilibrium. But the thing is, since I have values for all 3 of them, I don't really know if we're going in the forward direction or if we're going into the reverse direction. Meaning, I don't know if I will subtract by a number or I will add to a number of this. So in order to figure that out, remember, we always have to compare the Q value with the Kc value. So from these amounts, I have to find a Q value. And remember, a Q is the same equation as the K value, right? So let me just get rid of this. And now I wish I could have saved the formula, but we could quickly just write it out, right? Instead, we're just going to write it as a Q. But Q, remember, is products over reactants as well. So Q equals concentration of products. We already did this, right, guys? So this would be SbCl3 times the Cl2 divided by the SbCl5. That wasn't so bad. Okay. And now we have this number for both the SbCl3 and the Cl2. Maybe I'll just bring this down a little bit. And then this value for the 6.44 times 10 to the negative third. And we have to find out what the Q is. So let's go for it. Actually, I'll put it maybe down here. Q equals. So I have 0.0200 times by 0.0200, close that up, divided by the 6.44 times 10 to the negative third. Okay, and then let's get that Q value. Okay. So 0.02 squared, because that's basically what it is, divided by 6.44 times 10 to the negative 3. Okay, I will round to 3 sig figs, so 6.21 times 10 to the negative 2. All right. So now we have to compare the Q value with the Kc value in order to determine which direction am I going. Am I going to be going in the forward direction, or am I going to go in the reverse? Well, let's see. There's a little trick here, guys. Remember, if you want to compare, put the Q value on the right side and the K value on the left. The Q value we just found was 6.21 times 10 to the negative second, and the K value was what we found out in the way beginning, right? The Kc was 2.50 times 10 to the negative second. Now, since the exponents are exactly the same, we don't even have to pay any attention to them. I would just look at the numbers in the front. So since a 6.21 is greater than a 2.50, we can say that the Kc, if this is the smaller number, is less than the Q, right? 6.21 is greater than 2.5, and remember, the alligator, the teeth, are always pointing towards the bigger number. But now here's the trick, guys. Whenever you write this down, just treat this as an arrowhead and pull it back. Look, you made the direction. Since Kc is less than Q, we know that we have to go in the reverse direction. So in order to establish back equilibrium, the general arrow is this way. And if that's the case, all of the reactants will be decreasing and all of the products are now increasing. So in order to set this up, let's pause the video if you need to, and just write down, the Q's, because this has to be going because we need more room. So bye-bye. And actually, we don't need these initial values anymore. So I'm going to just get rid of these, because what we're going to do now is we're going to make an ice table. These are now acting as the starting molarity because we're changing back to equilibrium. So these are your new starting molarities, and since we're starting, I need that ice chart. Remember, I stands for initial, and we want to get to equilibrium. Now C stands for the change, and that's why we had to figure out what direction we were going. I didn't know before if we were subtracting or adding on this part. But since we now know that the direction is this way, I'm going to be making the reactants and I'm going to be dropping the products. If we are making the reactants, the change has to be in the positive direction. And for these, it has to be in the minus direction. So maybe I'll just say positive and minus. But now we don't know what the value is, right? I don't know what change there is or how to get back to equilibrium. So we use the variable that we always use as x. And since all of these are a number one coefficient, this would just be plus x, and minus x, because technically it'd be like plus 1x because you have a 1 in front of here, but no one says plus 1x, right? E is equilibrium, and this is equilibrium, and this is just the summation of what's going on from your initial to your change. So it would be 6.44 times 10 to the negative 3 plus x. I'm not going to state the unit because it gets a little hairy here. And then this would be 0.0200 minus x. You just sum that up. And then I'm going to get rid of this because we don't need this anymore because we know the general direction. And then this would be 0.0200 minus x. Now we plug the equilibrium line into our Kc expression. And since these are equilibrium values now in terms of x and numbers, I can now use this K value. So let's see. I shouldn't have erased that thing, but it will just take 2 seconds. But as you can see, this is one crazy question, guys, right? Okay, so it'd be products over reactants. So SbCl3 and then times Cl2 divided by equilibrium, right, of SbCl5. And now we just said as before that the top numbers are going to be the same, right? 0.0200 minus x And then the bottom is going to be the 6.44 times 10 to the negative 3 plus x. And the k value, which is what we found out before, is 2.50 times 10 to the negative second. Now, some of you might say, well, maybe we can neglect this x. There are cases in which we can neglect the plus x, but in this case, since they're both starting with values, and you have plus and minus x, and the k value is not really that small, times 10 to the negative second, you cannot neglect the x. So unfortunately, we have to keep the x's in there and work with the math. So let's do this. 2.50 times 10 to the negative second equals, now, since we're multiplying this by the same number, actually, I'm just going to work that out. So 0.0200 minus x, and then the same thing, right? 0.0200 minus x, and this is all divided by 6.44 times 10 to the negative 3 plus x. Okay, so this is going to get hairy, guys. We can probably already determine what's going on here. We're going to need to use the quadratic equation. So let's see, how can I simplify this? Well, let's first get rid of this. We don't need this anymore. So just pause the video if you need to write anything down, but I have to get rid of some things just for the sake of, space here. So this we're getting rid of. This we're getting rid of. And if I can, I don't know if I can, but I think I can. I think I can. Oh, hold on. Let's see. I think I can. Beautiful. I'm just going to resize this. Okay. And I'm going to put it over here. Remember, we're trying to just solve for the x values here. All right. This is crazy. So this is cross multiplication, right? This times this, and then these two multiplied by each other. So I'm going to try to, I'll make this a little bit clearer. It's this times this, right? And then technically, remember, since this is over 1, it would be these two times by 1. Okay. So let's do the top part first. Actually, we'll do this cross first, right? So 2.50 times 10 to the negative second times 6.44 times 10 to the negative 3 plus x. This is distribution, right? You have to be fair. This has to be times by this and the x value. So I'm going to write my answer up here. So I have 2.50. Actually, hold on. We have to multiply this, right? So 2.50 times 10 to the negative second times 6.44 times 10 to the negative 3. So I get 1.61 times 10 to the negative 4th plus 2.50 times 10 to the negative second x. And this is going to equal now just this times 1, right? But this looks like a foil to me, so I'll do it down here. 0.0200 minus x times 0.0200 minus x. This first term has to be multiplied by the first and the second term. You got to be fair. And then this has to be multiplied by the first and the second term. So let's see. Maybe if I could pull this over a little bit. Okay. So 0.002, actually 0.02 times 0.02 is 4. Maybe I'll make this. Okay, so 4 times 10 to the negative 4th minus 0.02x minus 0.02x plus x squared, right? Now I just need to simplify the like terms. So this would be 4 times 10 to the negative 4th minus 0.04x plus x squared. And this now all goes on this side of the equal sign. So 4 times 10 to the negative 4th minus 0.04 x plus x squared. And now since we have x values and x squared values, I now know that I have to do the quadratic formula, which means that I have to get all the x's, all the x squares on one side. Generally, we like to have a positive x squared, so what I'll do is I'll just move these two values over to this side. So by doing that, I would have to subtract 1.61 times 10 to the negative 4th, and that will go over here, minus 1.61 times 10 to the negative 4th. That will cancel this out. And then I have to minus 2.50 times 10 to the negative 2nd x. So minus 2.50 times 10 to the negative 2nd x. And we now have everything on the one side. And I'm going to just label it as x squared plus x and then the number, right? So the x squared comes first, and it's only 1x squared, so it's just x squared. Now I'm going to just gather up my x values. So it's a negative 0.04 minus 2.5 times 10 to the negative 2nd. So this would be minus 0.065x. And then I have to do this math. So 4 times 10 to the negative 4th minus 1.61. 4 times 10 to the negative 4th minus 1.61 times 10 to the negative 4th. I get a plus 2.39 times 10 to the negative 4th. And this all equals 0. And now we're ready to do the quadratic formula. So pause the video if you need to, right? So get rid of this. Goodbye. Boop. This we don't really need. I don't think that it's really going to interfere with anything. But maybe we'll just get rid of it. And then what I'm going to do is I'm actually going to get rid of this because I want to move this up. Okay, so now we're working with this only, right? So let's label out what A, B, and C are. Remember, the A value is in front of the x squared. The B value is in front of the x value. And the C value is in front, or actually the C value is just the random number at the end. So since there's no number in front of the x squared, remember that just means 1. So my A value is 1. My B value, you have to take into consideration that it's a negative. So it would be a negative 0.065. And the C value, this is positive. So I could just say C equals 2.39 times 10 to the negative 4th. Now for all of you that have the periodic table, for all of you that have a quadratic formula in the calculator, all you have to do at this point is take the A, B, and C value, plug it into your calculator, and then the calculator will, spit out the two x values. You always pick the positive number. Get rid of the negative one. In this case, though, we might get two positive values. I don't know. But for all those that, want to work with the quadratic formula, let's just do it. Remember, the quadratic formula is x equals negative b plus or minus the square root of b squared minus 4ac, and that's all over 2a. So let me just get rid of a little bit of this. So maybe I'll just put that as a reference over here. So what I'm going to do is I'm going to use this formula and just plug in my A, B's, and C values. So we have x equals b, which is this, right? And it's a negative b, but this is negative, so it should be a positive value. So it should be 0.065 plus or minus the square root of b squared. So I take the same number, negative 0.065. Now this is minus 4 times the a value, which is 1, times the c value, which is the 2.39 times 10 to the negative 4th. Okay. Oop. Hold on. Maybe I can squeeze this back in. Beautiful. Okay. All under that square root. And then this is all divided by 2 times a, which is 1. So we can simplify this. Generally, we could simplify this first, right? 2 times 1 is just 2. So I could get rid of that. Beauty. And now I can plug in everything here under the radical to get one answer. So that's what I'm going to do. So I'm going to say 0.065 squared. Remember, a negative times a negative is a positive. So it doesn't really matter that this is a negative value. We're going to get a positive out anyway. Minus 4 times 2.39 times 10 to the negative 4th. Okay. So I'm not going to round, but I am going to get rid of all this. Beautiful. It's a beautiful thing. This is 0.003269. Let's take the square root of that. And I'm going to try not to round, try not to round as much as I can. So I have a new number of 0.057175. That's enough. Let's cut this off. Let's bring this 2 under here. And I'm just going to scooch this over because at this moment now, we have to divide the formula. Our x value can have 2 answers because one is going to be the positive and one's going to be the negative. So in this case, I could have 0.065 plus a 0.057175 all divided by 2. And then I could have the 0.065 minus the 0.057175, and that's all divided by 2. So let's get those 2 answers. X equals, and then x equals. Let's see. Let's do the top one. 0.065 plus 0.057175. That's all divided by 2. Divide that by 2. Okay, so we get 0.061, and maybe here I'll round. So I'll do 0.611, and then let's do the other one. 0.065 minus 0.057175 divided by 2, and I get 0.00391. Okay, so pause the video because I'm going to get rid of all this. Basically, we had to do all of that mess to get my 2x values. So just pause the video if you need to. Because now we have the 2x values and we have to compare. Now remember in the beginning I said if you generally see a negative value, you could throw it in the trash. But here we have 2 positive values. We need to figure out which one is the right one. Well, we can't have an x value in which when we do the math will give us a negative molarity, right? Because there's no such thing as a negative molarity. So let's focus on these because these are the ones that we're subtracting. So let's see. If I do 0.0200 minus this as my x value, this is not good. This will give me a negative molarity. That doesn't make any sense. Let's just double check because we always want to, make sure. If I do subtract the other x value, I will get a positive answer. So by this x is not the right one. This is the correct x value. Because on the consensus that you can never have a negative molarity at the end of the day. Okay. So I'm just going to get rid of this. That was just like a little quick thing just to know which one is correct. And now I'm going to do the actual values. So let's just plug in everything here. I'm just going to compartmentalize. So I have SbCl5, I have SbCl3, and then I have Cl2. So in this case, I'm just going to plug it in for x, right? So 6.44 times 10 to the negative 3, it was plus x. And maybe I'll just go across the board here. This was minus x, and this was the same thing. 0.0200 minus x. Okay. Now I'm just going to plug in the x value. So 6.44 times 10 to the negative 3 plus 0.00391, 0.0200 minus 0.00391, 0.0200 minus 0.00391. Okay, so let's see what our new molarities are. 6.44 times 10 to the negative 3 plus 0.00391. And I get a new molarity of 0.01035 molarity. Okay, so that's for the SbCl5. Let's see for the other ones. 0.02 minus 0.00391. For both of them, I get 0.01609 molarity because they're the same math. Okay. Now, is this what they asked for? How many grams? So we have to now take these molarity values and just transfer it into grams. So, pause the video. Again, I'm so sorry for doing this, but I hope it clears up the space. I'm going to get rid of this because we don't need it anymore. I'm going to get rid of this because we don't need this anymore. Whoop, that was a little bit too... There we go. I'll get rid of this. And the only thing that we basically need are these three things. Now remember, molarity equals moles divided by volume. But now they told us that it was a 2-liter flask. We have the molarity. So for each one of these, I can solve for the moles. And remember, if I just rearrange this formula, moles equals molarity times liters. So I could basically take these values and times it by the new liter. The 2 liters, not the 5. The 5 was the initial. The 2 is now what we're in. So I'm going to take the 0.01035 and times it by the 2 liters. And then 0.1609 times the 2. And this will get me the new moles. So let's see. And maybe I'll just say that this is moles equals for each one of these, right? It's molarity times liters. Whoop. Okay. So now, okay, 0.01035 times 2. So now I have 0.0207 moles of SbCl5, 0.01609 times 2. I have 0.03218 moles of SbCl3, and then the same number here. Okay, of Cl2. But we're almost there. They want grams. So remember, we just have to convert from moles to grams. Now remember, if you want to do moles to grams, we can always do the conversion, right? Or we could do the quick-hand version because we're not in that chapter anymore. There are tricks, right? If you want to go, and maybe I'll put it over here. If you want to go from moles to grams, all you have to do is just times by the molar mass, mm, right? So once again, we just have to find the molar mass. I'll do it quick for you. And each one of these, all we have to do is just times by the molar mass of the thing that we're talking about, right? So the SbCl5, the SbCl3, and then the Cl2. So let's just quickly find out those again. So you probably have them on your paper, but I don't. So, but you're just going to times by those numbers. So let's see. The first one, oh yeah, 299. So you would times this by 299.05. The second one, you have 1 antimony, 121.8 plus 3 times 35.45. You get 228.15. These are probably going to be the same numbers that you saw before. And then 70.9. Okay, so 0.0207 times 299.05. Now I'm going to round to 3 sig figs. So we have 6, and maybe I will put this in blue, 6.19 grams of SbCl5. There's one answer. So we have 6.19 grams of SbCl5 in the new equilibrium with the 2-liter flask. Let's check for the other ones. 0.03218 times 228.15. I get 7.34 grams of the SbCl3. SbCl3 in my new equilibrium mixture. And then 0.03218 times 70.9. I get 2.28 grams of Cl2. Oh my goodness. Whew, guys. I'm so sorry. Sorry. I hope this helped. Please, if you wouldn't mind, please press the subscribe button. Thank you so much. That will be, amazing. You guys are great. I appreciate you guys so much. And I'm so glad that, my brother and I can help you in learning the subjects that you need to learn in school. Right now, we have physics videos and math videos also. So if you're taking geometry or algebra or pre-calculus, we might be able to help you. All right, and physics as well. So go check the channel out. But I really do hope that this one helped. If you guys can do this problem, you got the equilibrium chapter. So it covers everything, all right? So thank you so much, and I will see you all in the next lesson. Okay, bye-bye.